the speaker. So I'm happy to welcome Pawel Bruckman. He will talk about the globally square alignment with Kalman Filter fitted tracks, and I'm really looking forward to it. You have 25 minutes, Pawel.
Okay, thank you, and sorry for the hiccup. Okay, so I will be talking about something that is, okay, don't expect novelties. These are all very old ideas. It's rather an attempt to gather some ideas and present you with something that I hope might have some pedagogical value at the end. What's the aim? Why do we bother at all? So various customers rely on least squares fitted track model. And I would say the prime example is the global approach to alignment, so-called global chi-square alignment. However, experimental tracking realm more often implements Kalman filter, of course, for fitting tracks. And so the frequently asked question is, can Kalman fitted tracks be used safely and efficiently for the global chi-square alignment, and at what cost? Well, in the following, I used these references here if you wanted to look up the details. Now, important note is that really, in case of alignment, tracks are not the prime objects that we are interested in. Tracks are treated as surveys, as gauge tools only. And this is the sort of guiding theme of the talk, of the rest, which is actually very short. Let us compare two track models, right? The global chi-square track model, least squares. It's a global approach, and it's based on minimization of the chi-square, which is defined in an obvious way. We have residuals which contain the actual residuals of the measurement plus deflection angles and the corresponding covariance matrix, which is explicitly diagonal, representing measurements and uncertainties on the scatterings. Track is parameterized by a single set of global parameters and 2 deflection angles per material surface. That is how it's typically done. So it's 5 + 2n. Now on the Kalman filter side, okay, the fit is done completely differently. It's based on forward filtering and backward smoothing. And track is represented by n state vectors and their corresponding covariance matrices, which each one corresponds to typically a measurement plane. So we have 5 times n track parameters. We have, of course, residuals, which are defined in a similar way, while the scattering, these are only residuals because the scattering contributes just to the process noise. Let me introduce again very briefly the global chi-square alignment basics. So the idea, it's again exactly as for the track fit. It's minimization of the global chi-square, which is basically the sum of the chi-squares for the tracks concerned. And after linearization, it is solved in a usual way. However, the difficulty is that residuals are themselves function of track parameters and alignment parameters, while track parameters are themselves, of course, dependent on the alignment. So it's a nested problem. Okay, so with the several symbols defined here, what is important here is that the covariance, full covariance of the track parameters is an important ingredient in the problem. And the problem is, of course, the linear set of equations is solved by inverting typically, or some sort of inverting or solving of the big matrix. That actually itself is the weight matrix of the parameters that are to be determined. Now, the central item in this solution, actually, because all the properties of the solution of the alignment are actually encoded in the matrix. So the central object is the covariance of the residuals of the track fit. So it is of all the residuals for a given track, which is given by this expression here on the bottom. Okay, so let me again expand a little bit and check on the dimensions and the size of the objects that we have to deal with. So on the global chi-square side, okay, you know already the covariance. Now the derivatives of the residuals with respect to track parameters. Okay, these are typically pretty dense and highly non-trivial objects in the global model, because you have to find the dependence of all the residuals with respect to parameters of the track, typically defined at perigee somewhere at the origin. And in the presence of material and non-trivial magnetic field, it may be pretty complex. Track covariance, okay, I've already introduced it. It takes quite some number of operations to get. Now, Kalman Filter track model, it's seemingly simpler, especially the derivative matrix, the H, is trivial and sparse. Trivial in the sense that these are derivatives defined with respect to track parameters defined locally at the usually measurement plane, which makes it very simple. Track covariance itself has larger dimensionality because it's 5n times 5n, because it's basically correlates all the parameters of all the measurements on the track. All the parameters, so 5 parameters per each state or measurement plane, if you like. Kalman Filter can be considered as a Bayesian recursive process starting from some arbitrary, typically very soft prior, which then can be put to in the limit to none. And the diagonal elements, the CK, which are shown here, so the diagonal ones, 5 times 10, 5 times 5, are obtained in a standard way. So first we do the filtering, so we accumulate information along the measurements with the Kalman gain matrix. And what is very important in tracking is that we are interested in the best estimate of the track usually at the origin of the track or somewhere close to the interaction. Therefore, we have to backpropagate all the information, which is called smoothing, and this is done with smoother gain matrix AK. The latter is necessary, as I said, because of what we are actually interested in. Because already after filtering, our track parameters at the exit of the tracking system are optimally determined, but this is not what we typically need. Okay, so that's where actually tracking ends. This is what all tracking. This is all that tracking is interested in fact. However, it's not sufficient for alignment. If we want to do alignment with Kalman Filter tracks, we need full covariance matrix of the track parameters on all the states. So basically, all the blue objects that are here indicated on this schematic. The off-diagonal elements of C can be obtained recursively, again, using the already known calculated smoother gain matrix by a very simple recursive expression. The procedure requires actually 125 n times n minus 1 multiplications, provided the smoother gain matrix is already known or conserved somewhere after fitting. calculation of the R, so the full covariance of the residuals, appears actually faster for the Kalman filter thanks to sparse nature of H, as I mentioned already before. If several tracks have been fitted to a common vertex, and that's sort of another big chapter, the covariance of each track at the vertex position is modified by, of course, the additional measurement. And this can be propagated in a fully analogous way forward to the states at measurement planes to yield their full covariance. And this is given by this, expression. Is actually not very complicated. Important thing is this, the difference between the covariance after track fit and the covariance before, vertex fit and after the vertex fit, and then it's propagated and added to the original one, or rather subtracted, if we think of it. Then even more importantly, actually, for the alignment, that the vertex introduces precious correlations between any two states in any two tracks. And these can be obtained, again, in exactly the same way, where I, in this formula, I deliberately put zeros to show that originally, before we fitted the track, there was no correlation between two different tracks, and neither at any measurement plane nor at origin, so at the vertex. Okay, so let me show you, this is something that I always do to myself better understand what I'm doing. It's to analyze super simple example. This is a global chi-square fit, least squares, if you like, of a track, well, actually on a straight line through three equidistant points with a common uncertainty on each, sigma. So we have our covariance matrix or weight matrix in this case. We have residuals and their derivatives of the residuals with respect to track parameters. There are two track parameters and three residuals, and the H matrix in our case looks very simple, but still it's a dense matrix. And what I pointed out earlier, and actually this scales unfortunately with the problem. Now the C, so the weight matrix for the covariance matrix for the track is given by for this particular example by this 2x2 matrix, and the R, so the full covariance of residuals. There are three residuals, so it's a 3x3 matrix. Is given by here on the bottom. Okay, let me stop here and switch to the Kalman filter case. Okay, so we do exactly the same. However, the objects that we're dealing with are completely different. I mean, at least at first sight, because the residual derivative with respect to track parameters, mind that we have now 3 times 2. Representing the full track description, so 3 states, is given by this sparse matrix. It's very sparse actually, right? However, if we do the use the prescription that I showed on one of the previous slides, this is the covariance matrix that you will get for the track. Okay, it looks a little bit more complicated than for the least squares case, but this is actually quite misleading, because at the end you have to extract the R, so the full covariance, which involves these matrix multiplication, and because of the simplicity of H, it actually turns out to be even faster. And what is important, you end up with exactly the same matrix. So from here on, if you do the alignment, you don't care what kind of underlying tracking you used. Important is that you have the correct and the same R. So the full covariance of the residuals. And this is your ruler in the alignment problem. Okay, so let us solve this alignment problem. So our model is each measurement plane has 1 degree of freedom in vertical direction, very simple again. So we have the derivatives of the residuals with respect to alignment given by this relatively simple matrix. And then therefore the M, that you know what it is, it's the full well, weight matrix of the alignment parameters is given here. Oops, sorry. And here is the sketch showing again the problem. So we have 3 planes which can move up and down. We fit, and this represent the eigen vectors of the solution, which actually are listed here on the bottom. The matrix is, of course, singular, leading to 2 weak modes of the alignment solution. One is the global shift up and down, and the other one is skew, which corresponds to the tilt of the straight line. And the third one, which is kind of Sagitta, in this case, of course, is well constrained because we have straight line. Okay, so and this is not just the feature of this very, very simple example. It's a general feature. Alignment has weak or singular modes that we have to deal with. So weak modes can be mitigated by introducing well-motivated constraints. On alignment parameters, these are actually rather trivial, and I'm not discussing them here because they are sort of external to the tracking realm. They are applied at the sort of alignment solving stage. However, we can introduce constraints on track parameters or on track common vertex. Just to illustrate, of course, it's very it's well, very theoretical case. If we knew perfectly A0 parameters, so the tilt of this straight line, then if we again do the solution according to all the rules, we end up with still singular solution, but now only one weak mode, which is the total shift or translation up and down. However, the second one, of course, which corresponds to the tilt of the straight line, is already well constrained, so it's the lambda 2. So this is just to see how the constraint nicely works. Okay, but we can have also a little bit more complicated case, and this is actually the most involved one, which is when we start fitting a common vertex of multiple tracks. Okay, now here again a very, very simple case, even actually simpler than before, because we just have again 2 straight lines. We have one measurement plane at 2D, which so to say is fixed for simplicity, and we have 2 other which are close to the origin, to the vertex, which can move up and down. And now I'm using this formalism that was shown at the end of the formal discussion, which is the one that gives you the full covariance of track parameters, but for common one for all the fitted tracks. Well, in this case, there are 2. So what is shown in the blue is this actually crucial bit which correlates different tracks via the fitted vertex. Because the black are just the covariance matrices for individual tracks updated for after the fit. But the blue thing is the new quality, which is actually very precious to alignment. The matrix here is actually singular due to unconstrained vertex position, which is fine because this is what we want. We don't know where this vertex was, and we just want to constrain the two tracks to a common vertex. The other singularity is removed, of course, via the correlation between A and B, and good vertexing, therefore, should be assured. And you see the solution. So the one which is singular is the common motion or shift up and down of these measurement layers, which do not actually distort to first order the vertex. And the second one is well constrained, so actually the distance, or so to say, between them is fixed. Okay, and this brings me actually to already to my conclusions. Let me summarize it, saying that in problems like alignment, tracks are merely tools providing correlations between measurements. Kalman filter results in a track fit which is equivalent, completely equivalent to the least squares one, but is represented in a completely different model, of course, in a different way. The off-diagonal elements of the track parameter covariance matrix, which is actually the typical argument, difficulty in using those tracks. So the correlation between different track Kalman states can be recovered recursively with the smooth again matrix. The full calculation does not appear computationally more intense than in the least squares case. It may, however, be more numerically stable thanks to equal treatment of all the measurements and very simple structure of the H matrix. And the H matrix of least squares fit is dense and highly non-trivial. I already said that. And its extraction may be heavier in general. Constraints on track parameters can be introduced, as in the least squares case, by adding pseudo measurements in the filtering. Well, you can think of it as a meaningful prior when you start the filter. Any other constraints, vertex, invariant mass of the vertex, of course, can be equally introduced with full propagation to Kalman states, which does not involve large matrix inversions, as it would be the case if you wanted to do it in a global way. Imagine many tracks, each with many measurements, and trying to extract the covariance by means of sort of global fit, so least squares fit. That is usually computation more demanding. That's all from me. Thank you for listening.
Thanks, Pawel, for this very interesting overview about all the math behind the different approaches to track fitting and how it affects the alignment. This talk is open for questions, if you could raise your hand. Sarah.
Hello, Pawel. Okay, thanks also for the talk, very nice. I have, I mean, small details here on your talk. When you were introducing this matrix for the Kalman filter, I think it was in page 5. Okay, this is for all the measurements, right? So that's I mean, that's okay. The only thing is, in principle, okay, when we are doing tracking, we are only interested in the covariance at the PDG rather than in every.
Yes.
Your argument is that
which
you
is the
say,
question, because actually for tracking, as long as you are doing physics with these tracks, exactly, all you are interested in are the black objects, so the diagonal elements. So actually you get these diagonal elements, but possibly you are interested just in the one extrapolated to the vertex. Okay, that's fine. But this is not what alignment needs, right? Because the alignment is concerned with every single measurement on the track. That's the thing.
Yeah, no, and then okay, that's my question. Then I mean, this is really how you correlate the measurements in every of all the measurements along the track. So
yes, of course. Just exactly, you get as what I tried to demonstrate is that you get exactly the same result as if you did the fits in the global sense. So basically inverting the weight matrix.
Okay. Yeah, Sava, continue.
Okay, well, I have a second comment, is that, well, okay, you demonstrated, or you showed that, okay, these vertex constraints can do a lot of good for the alignment, because yeah, it adds removes some weak modes, and also it adds correlation between different parts of the detectors and so on. However, that's a bit more tricky, because when you want to do a vertex constraint, you know, especially when we have pile-up, etc., etc. So it's not so easy to say all the tracks come from the same vertex. So there is some kind of selection there that could be a bit of dirty.
Yes. Okay, I'm not entirely sure what you're aiming at, but basically, let me comment here. We've had a lot of thinking and discussions, I think, about it, how to possibly use, because it's also technically doable with the least squares fitted tracks as we use them now. The problem is, of course, this physics motivation. So to really select things properly. Now, this is not a suggestion to use every single track for vertexing. No. Usually, most of the tracks and the baseline alignment you usually do by using, you know, single tracks or whatever. But you might basically find a way to define very carefully selected events where you can combine them into a reliable vertex, primary or even secondary vertex, like I don't know, Z to mu mu, and this will basically fix very important weak distortions of the alignment. The other tracks which are not used for vertexing, of course, do not disturb it at all. They just don't contribute to solving this particular mode. But it's important to have at least a handle, some handle at some point over this. And vertexing, of course, is by construction the best to assure good vertexing, right? So good reconstruction or optimal reconstruction of the input parameters. So
okay, thank you very much.
There is a lot of distortion that well, okay, yeah, I don't have plots here, but that basically distort it, and these are weak modes.
I think in the interest of time, we defer the further discussion to the discussion session next week. Thanks again, Pawel.
Thank you very much for allowing me to present this.
If you could unshare your slides, and the next speaker could bring up the slides while I'm introducing him.
Yeah, that's okay. It's another stop share. Okay. Does it work?
Yep.